Hi everyone, today we're going to work on volumes by creating them using cross sections. So this is not done by rotation. Sometimes the objects do look like they're being rotated, but it's really just building almost like from the ground up. You can almost say like growing crystals. Or if not, you can say, if you ever take a cucumber and you start slicing it in slices, this is kind of what the model looks like. So we take our regular graph, and let's say we're going to do a parabola like we did before. I'll call this y is equal to x squared. And from this, instead of doing a rotation like we did before, we ended up with a volume. Or we take our 2D shape, making it into a 3D shape. We are instead going to build up using geometric shapes that we know already. So the ones that we're going to use today, we're going to use a square. We're going to use a semicircle. We're going to use an isosceles right triangle. And then we have two versions of this, okay? We're gonna have it sit on his hypotenuse and also on his leg. Okay, two versions. Let's do that as two versions. One version of using a hypotenuse and two using a leg. Okay, so we'll work on these three examples today. So here we go. So the idea is that we are going to build on top of this using the shape. So let's say I use a square. The square is going to be built up, standing vertically, perpendicular to the base. And we're going to keep doing that. Draw another square. And see this square over here, since the base is longer, so the square is going to be even bigger. The base here is smaller, it's going to be a smaller square. Okay. And what happens, it ends up coning out here. You look here like that, kind of like this little image here. So depending on the shape that we use, it changes our 3D object shape and also changes the volume, of course. Now, how do we do this? Just like before when we talked about finding volume, the idea of a volume is, in a basic geometric way, is just the area of the base times a little bit of thickness. So we take one sliver here that was cut out, and this is just a square. This is let's draw a little better. Since we're building these volumes based on squares, this is really S by S. But this is a 2D shape, so to give it a little depth, I'm going to give it a little depth here to make it into a 3D shape. And we're going to multiply this by a little bit of dx, and that's going to be our width. And what we're going to do, we're going to stack these objects behind each other. So the next object is going to go back here, and the next object's going to go up here. And when we stack them together, it ends up forming this 3D shape. And this 3D shape, we can calculate the volume. We're trying to get as small slivers as possible. That's why we're multiplying each of these widths by a little bit of dx. But pretty much it's just the area of the base times width. Or a little dx. So our big deal here is figuring out what our area is. If we use a square, the square is done by s squared. A semicircle is 1 over 2 pi r squared because it's half a circle. Isosceles right triangle, we'll talk about that a little bit later. I'll demonstrate to you guys how we came up with that. It's actually very quick and easy. But each of our geometric shapes, we have a way of talking about and calculating it. So let's go back and try to finish our example here with y is equal to x squared. Let's go so find the volume using cross sections for y is equal to x squared between, we'll say, 0 and 1. Okay? And we're going to use squares, using squares. Let's go back and build that model quickly. We had our parabola. So now I'm going to actually try to draw this in a 3D way, where this is my x, y, and call this z for popping out. And the parabola was drawn something like this on the floor. So if you can see, this here is my x and y axis. It's almost like a sheet of paper sitting on the floor. and we are going to build shapes coming out of it. So we're going to build a square. Oops, sorry, this way. Nope, a little more. We're going to build straight up, forming a square. And the next one is going to be building straight up. Oops, that should be smaller. Okay. And we're going to add up all these little shapes. And what happens is when we're talking about adding things together, the integral is super important because that's our cumulative change. So the volume of the shape will be the integral from 0 to 1. And what are we adding? We're adding area times a little bit of width, because that gives us our volume. Sometimes we can say, oftentimes we see it as area times height gives you volume. But I feel like height is oftentimes going vertically, just the way we picture things. So I'd rather call this more like width. So the area of this shape is s squared, and the little bit of width is going to be our little dx here. Now the complicated part is figuring out what your s is. What is this value here? What is the s? But lucky for us, in this problem, the s is actually the same distance as this function. And that's one of the key things to note. Oftentimes it is just the f value, the y value. What is this y value? What is that length? And in this case, that's just the function x squared. So our s value here, s for our sides, is actually the equation x squared. So if my value at 1 is 1 squared is 1, well, so is the height of my square. So it's 1 times 1. So the area is s squared, and we're going to write that as, x squared. We're going to square that for a square to find the area of a square, and then multiply that by a little bit of dx. And that's the setup. This is it. What this integral will do, it will plug in the 0, multiply by a little bit of width, then plug in like the next point next to like 0.01, then 0.02, then 0.03, and 0.04. And it'll add up all the little rectangles, or sorry, all the little squares, and it will then add up the volume together, giving you that full shape. Okay, let's try something a little more complicated. What if we did a square problem? Y is equal to a square root of x problem. So we'll draw this very similar to what we did before, where the square root problem will kind of curve out like this way. Okay, sitting on the floor. Okay, this here is my floor. Trying to draw this in a 3D way. And then we're going to build squares from this. To build a square, let me use a different color here. My square is going to come popping up since it's a square. Okay, and we're going to build an infinitely many set of these. And when I stack them together, it's going to kind of give you this curve object here going on. Okay. So to find the volume of this, we're going to simplify the problem. The volume is just from the starting to ending of our function here, squared dx. Because in this case, the function is also the same value as the side, s. The function is just given as x squared of x. So the volume is from a to b, we'll say from 0 to 1 again. And it's going to be square root of x, because that's the length here, right here. That's the length of s. And we're going to square that because s squared is the area of a square. Multiply that by low dx. And that is the setup. Let's do one more. What if I asked you to bound it by two different functions? And let's say on top is between y is equal to x squared, and the bottom y is equal to negative square root of x. So let me draw this out. Remember, this is a sheet of paper on the table. So to draw x squared, and to draw a square root of x. So two different graphs. So these are our boundaries. This is going to be our top and our bottom. So if let's draw one shape here, one square. Oops. From top to bottom. So then the square would come up here. Okay. And then following the square, let's draw a small one behind it. Okay, building that 3D model. Coming up. So let me get rid of that just so we can just be a little cleaner now. So how would we find this volume? It doesn't change what we're building our model with. We're still building it with a square, so we're just adding up slices of the square. We just have to figure out what the area of the square is. So to talk about the area of a square, we need s squared, which is the reference to the side. The side is this value here, the top function all the way to the bottom function. We've described how to do that before. So s is the top minus the bottom. The top function we said was x squared, and the bottom function is a negative square root of x. Looking at the minus sign and the negative sign, those will make a positive. So it turns out the square root of x adds to x squared, increasing the length. Yeah, and that's right. It does increase the length. The top value is increased by the bottom value here. So this is my s value. So to talk about volume, volume is equal to the integral, where we said from where we're going to start and end. We're going to start at 0 and end at 1. The s squared, right, where we said we're going to build this with squares, this is going to be our full x squared minus square root of x, because that's the full length of my side here. That's the full length. I want to keep that full length. Squared and then dx. Now, how do these models change if I use a different shape? Well, let's go back up here and take a look at our first example. Draw a little slash here. What if I use a semicircle when I'm building this model? Okay, so I'll end up trying to draw this right here, doing my best. We said parabola looks like that. And let's go ahead and build the shapes out. We're going to use semicircles. So take a look. It's going to be a little bubbling effect here. That's half a circle, right? Some bubbling effect, right? Okay. Can you see those semicircles being built out? It's half a circle. So our goal is to figure out how to find out what that area equation would be for the circle. Now, area of a circle is described as pi r squared. When we're talking about semicircles, we're just going to divide this in two. Now, the key grab here is that to find the area of a circle, we need the radius. But when I'm looking here, is f of x, is my y value the radius of this semicircle? Let me zoom in a little bit if I can. No, I can't zoom in. Is this radius, let me zoom in, let me draw this again real quick, just so you guys can see this. This is my semicircle. Is this y value here my radius? Remember, the radius is half the circle. So there is a gimmick again for all these shapes. And this one is that the radius is not the full y. The radius is half of your y. It's half of your function. Because if the full value, the y value, is the diameter of your semicircle, then the radius would just be half of it. So let's go ahead and do something here. We're going to write our equation. We said this equation that we're bounding by is x squared. So if the diameter is x squared, the diameter is x squared then the radius has to be x squared over 2. When we plug this into our area equation, area is equal to 1/2 pi x squared over 2 squared. Simplifying this a little more, I'm going to square the x squared over 2. That becomes x to the 4th over 4. So plugging this back in, area is 1/8 pi x to the 4th for this specific equation. Writing the integral equation, we are adding semicircles with a little bit of dx. Adding semicircles with a little bit of dx. So our integral between 0 and 1 is going to be 1. Our volume equation is 1/8 pi x to the 4th multiplied by a little bit of dx. This equation looks slightly more difficult. It does because of the pi r squared nature to it. But let's go ahead and simplify some of this. If I get rid of the 1/8 pi because these are constants, we're left with 0 to 1 of just x to the 4th, which is, in fact, what we wrote before. Let me finish this up. 0 to 1 of x squared dx. It looks very, very similar to our answer back here. And that's actually a similarity that we're going to see with all these problems that we're going to do right now. They're all going to have this y squared idea, this function squared idea, with a little bit of changing of the constant values depending on the shape. So there is actually a key online where you can find out all the quick cheat sheet of all the different volumes, cross-section volumes. They're practically the same equation with just the constants changing so that they match that new shape. Okay? So we still have that x squared, or that side squared idea. Okay, let's go and jump to another example. So let's do our square root of x version with semicircles. So we're building out semicircles. Let me draw this as best as I can. And we are going to build out semicircles. So that's my semicircle. Okay, semicircle. So to find the volume of these semicircles, I'm just adding up the areas of these individually. So the volume is equal to the integral from 0, let's give you the generic, from a to b of pi r squared, and we're going to throw 1/2 in front of that because it's a semicircle, and then a little bit of dx, little slices. We want to go ahead and figure out what our r value here is, because the r value isn't the y value, it's half of it. So it's going to be the square root of x over 2. That's my radius. Again, that's to talk about y. Square root of x is my y value, the full length. Over here, that's the full length. But we don't want the full length. We want to cut that in half because we just want the radius. And now that we found the radius side, we can just plug it in. So integral from 0 to 1. I'm going to throw the 1/2 and the pi on the outside because those are constants. And the r squared would be square root of x over 2 squared dx. I'm going to square the bottom, the 1/2, and that's going to be 1/4. I'm going to throw that out. 1/8 pi integral from 0 to 1 of square root of x squared dx. Oops, not one. Does this equation here look somewhat similar to what we wrote for our last problem when it came to semicircles? Do they both have a 1/8? Do they both have a pi? The only thing changed was the function, where the previous problem had an x squared as the function, and our new function was square root of x. So one thing that we can take away from this is that they're going to have similarities, and there's actually a general rule. And the general rule is the volume for semicircles will always be 1 over 8 pi integral from a to b of your function, whatever that function is, squared dx. Or if you don't want to use y, because it's not always y, you could describe it as the side squared. Whatever the side that's going to be sitting on that base. Does this change for my next example, the one that we did right here? Are we going to be expecting the same type of formula? Okay, let's talk about it. We said the upper was x squared, the lower was negative square root of x. Okay, so let's go and draw that again. We had the upper of x squared, lower of square root of x. I'm going to take one cross section as an example. So this is going to be x squared and negative square root of x. To build a semicircle, that's half a circle. Looks kind of like a rainbow. Blend that out. So the volume is equal to, let's start from scratch, from the integral from, let's say, 0 to 1 like we did before. And we want to find semicircles, so that's going to be 1 over 2 pi r squared dx. We know the 1/2 and the pi, these are constant, we can throw these out. Volume is 1 over 2 pi, integral from 0 to 1. And what is our r value here? Let's take a look at our r value. The r value is not the full length, it is half that. So the full length would be x squared minus a negative square root of x. And we're going to divide this into half of that. So we plug that r into the value for r squared. It's going to be 1 over 2 x squared minus, oh, let's do a plus, square root of x squared with a parentheses dx. I'm going to square the 1/2 to kick it out because it's a constant. That'll be 1/4. And 1/4 with a 1/2 on top, on the outside, is 1 over 8 pi. And we have the integral from 0 to 1 of x squared plus square root of x squared dx. And turns out that's very similar to what we had written over here. X squared minus square root of x squared. Except we have a different constant in front due to the shape. So this brings me back to the point. For a semicircle, this equation is really going to be the volume, 1 over 8 pi, the integral from a to b, where you want to start and where you want to end. And it's really just what we call s squared, where s squared refers to that full length from top to bottom of that slice. Now, does this change for the other shapes that we're going to talk about? Well, let's look at what the equation of a isosceles right triangle is. So isosceles right triangle, if I draw it this way, and this is going to be with the leg as the base, we'll call this S, S, and if you remember in your pre-calculus and geometry, this is 45, 45. This is s square root of 2. That's how we get around there. That's just related by s squared of 2. Just to know this. Okay, again, the sides are s and s. This is a right isosceles. Oops. Triangle. Right isosceles triangle. Now, how can I find out what the area equation for this guy is? Well, this almost looks like a square, doesn't it? Doesn't it almost look like a square? Except it's just half a square. So it is a square, but with a 1/2 in front. So it turns out to find graphs, to find volumes, we could build triangles darn it. Sorry. Drew that low too quick. Draw triangles rising up here. And this would be described as 1/2 s squared, where s is that full length, that side there. So how would we plug this into the volume equation? The volume is equal to the integral from a to b of our area of our base times a little bit of width. Our area of our base is 1/2 s squared dx. The volume equation for a right isosceles is 1/2 a to b of s squared dx. Does this equation look familiar? We're back to having that s squared equation, except this time having a 1/2 in front. What if I shift this around and have the hypotenuse? This is something that kids struggle looking at. Instead of having the leg sitting on the graph, what if I have the hypotenuse sitting on the graph instead? Like it fell over. Right? The hypotenuse is sitting on the graph instead. Well, our goal again is to find that area equation. If I call this S, what would this area equation look like? So a lot of people come up with this actually really good trick. If this is S, how could I use that to find the area? Well, the trick was this, to build out a square. We said these were 45. Wasn't this 45, 45, 90? 45, 45 is it makes it a 90. It turns out this is really a square. Area is s squared, but I only want 1/4 of it. So how would a right triangle volume equation? This one is a kind of standing up on the leg. This one here, the volume would be lying flat on the face. It would be 1/4 integral of a to b of s squared dx. So the only part that changes is that constant in the front. And using these gimmicks of saying, hey, this is up here, this is really a square, half a square. This here is really a square, but 1/4 of a square. We're able to use that s squared idea again repeatedly, over and over and over again. Now I just want to do one last quick example. If I gave you with a problem, let's take a circle. So x squared plus y squared is equal to 4. That would give us a circle graph with a radius of 2. Right? I'm going to solve for y, and I'm going to say I just want the top of the circle. So it will be 4 minus x squared. And I just want the top of the circle, okay? I'm going to build the volume of this top of the circle using all 4 shapes. And we'll do this super quick. The first question is, what is my s value? If I want to build a shape, let's start off with the easy square. What would the s value be? The s value would be just the equation. S would equal to the square root of 4 minus x squared, right? That is the function of my graph. So let's talk about the volumes. The volume we're going to use squares first. Well, isn't the volume equation just integral of s squared dx? S squared is just our square root of 4 minus x squared dx. To deal with semicircles, the volume is 1/8 pi integral of s squared dx. How did we come up with that? We said that the r value was half the s value. And when we say pi r squared, this is going to be squared. So it's going to be pi 1/2 s squared, becoming 1/4 s squared. And do we really want a full circle? Nope, we want half a circle. We end up with 1 over 8 pi s squared. And that's our base here. So this problem would be volume is 1 over 8 pi integral of square root of 4 minus x squared, which is our function value, our y value. How about our right isosceles triangle with the leg on the base, sitting this way? This is my leg. This was going to be 1 over 2. The volume is 1 over 2 integral of s squared, which is for us 1 over 2 integral of the square root of 4 minus x squared dx. And our last one, this is for, the isosceles, right? With the leg on base. Next one, isosceles, right? With the hypotenuse on base. So this one's the one that's going to be sitting flat, or that's my S value. And this one's going to be the volume is 1 over 4 integral of s squared dx. And we just plug it in of square root of 4 minus x squared dx. If you look at our 4 answers here, they all, If you look at our 4 answers here, they all have the same s squared property. S squared, s squared, s squared, s squared. The constant in front changes depending on the shape. Okay, thank you very much.